because I can't. That was a whole few days ago. It was somewhere here, right? Oh, let's make sure audio is good. Did we hit variables? Or is that right where we were?
I think that's
right where we were. Perfect. That's what I had a feeling. Okay, cool. So, just as a refresher, we were talking about values, and all the values have a type. So you could have like words, we call them strings, and they are strings. They have type string. We have integers. They're just numbers, but they're whole numbers, and they're type integer. And then we have the numbers with like decimals. We call them floating point numbers, and they're floats. They're a little different. And then we use this word literal to mean when you see like a value right there. When I write the number 1, it's the number 1 and has the value, like assuming it's an integer, it's the integer 1 with the value 1 because I wrote it, there it is. To a computer though, and this is very big, and at first, it's kind of hard to really give the appreciation for how good this is. This is a really good thing. But to a computer, the string 1, the integer 1, and the floating point number, like 1.0, are all different. Even though they're all 1, they are different. They have different types. Now, some things you can mix and match types. Some things you can't. And I think we already saw what happened when we tried to add a string and an integer together. Who remembers? It just said, I can't do that because what does that even mean, right? What is hello plus 7? Oh, that's a stupid question. So if I say, oops, print 1, oops. I mean, in the code, we could tell the difference. All right, we could tell, well, the first one's a string because it's got quotes around it. The second one's an integer because it's just the number 1. There's no quotes around it. And the third one's obviously a float because it's got the decimal. And the fourth one, well, that's also a string. It copies the float one. But as far as the computer's concerned, all of those values were different. But when you print it out, could you tell? No, you can't. You can tell the difference between the potentially float ones. Like I know the 2 on the right are not integer, or the 2 on the bottom aren't integers. That's the best I could do, but I still really don't know which one's which. There's a mystery there. Now, everyone pay attention to this because I may have shown this to you in lab, but I'm going to give you a big, okay, first let me show you this. Type of 1. So here's what I'm doing. I'm doing a little bit here. Typically, I don't like to write code where there's a lot happening in one line of code. That's usually not very nice because it gets overly complex. That's not just because you're learning. That's just a programming thing in general. But each line of code here has a little bit of extra stuff going on. I'm just going to run it so we can compare. First line, I'm saying print the string 1. And then the comma in a print allows you to just print multiple things out. It just separates them by space. And immediately after that, I'm printing out the type of what the string 1 is. And we see class stir. What does that mean? String. The next one, we see a 1 class int. It's an integer. Float, and then back to string. Great. So if you ever wonder what the type of something is, you can use this type function. It'll tell you. It gives you back that information. Class means like classification, let's just call it that. Int for integer, stir for string, float for floating point number. Okay. It's kind of it might seem kind of useless at this stage because we're asking the literal what its type is, and when you look at a literal, you can usually tell what it is. But once we get to variables, this will be a little more handy. Now, here's the big thing I want you all to pay attention to, because this is the root of a lot of bugs that new programmers have when using Colab. I love Google Colab as a programming environment, but there's one thing I absolutely hate about it for teaching new programmers. And it's that it tricks you into thinking it's printing things out, but it's not. If I say print 1 plus 1, what am I going to see as a result? 2, right? Because I printed it out. I said, what's 1 plus 1? 2, and then I immediately printed out the result. Great. Now, what if I just do 1 plus 1? I also see 2. But I didn't write print. But it clearly printed it out, right? But I didn't. And this is where the issue arises. Now, everyone really pay attention to this, because this will mess half of you up, even if you're listening. And that's okay. I'm expecting it. This always throws people off. This is something Colab does that confuses people. It didn't really print anything out. You're looking at it and you're like, yeah, it did. Not really. Here's what it really did. We have this value, 1 plus 1 gets evaluated to 2. And what am I doing with the value 2? Nothing. I didn't do anything with it. And so we've got this dangling 2, just kind of sitting there in that chunk of code. I hit run. It evaluates to 2. There's this 2 sitting there. In Python, we didn't do anything with it. So Colab is going, here. I've got this 2. You didn't do anything with it. I'm just going to just kind of like let you know it's there. But it didn't print it out. It looks like it did. It didn't. It just showed it to you. It's different. And I know it looks like it's doing the same thing as printing out the sum of 1 plus 1, but it's not. First, this only works if it's the last line and it's a dangling value. So for example, if I say print hi and I hit run, we don't see the 2 anymore. Because the last line didn't have a dangling value. The line above did, but it didn't care anymore. It's only if it's the last line and only if it's a dangling value. If I wanted both of these things to be printed out, I'd just tell it to print it out. There. Now, what I'm about to show you is going to be the most obvious thing, the most obvious difference. If I say 5, 5 is just the literal 5, so there's this value 5 floating around. I hit run, nothing was done with it, so Colab is going, here's a 5. If I say print hello, we see hello. Now watch carefully. If I just say hello, so I'm going to hit run, there's going to be this value, the string hello, that's just floating around, and it's going to get shown to you. But look, it actually is shown to you a little different. So this is the most obvious example that I can show you right now of how it really isn't printing it out. When you print it out, you just see hello. But when it's showing you the string, it's showing you the string, but it's also putting those quotes around it to be like, yeah, it's a string though. At the end of the day, the big takeaway from what I just said, if you ever want to display a value, use print. Don't do it like that one, that second box there. Do it with a print. If you do it with a print, this issue won't hit you. If you ever start relying on it just to kind of like show you information, you're going to be in big trouble. So whenever you want to display something, whenever you want to print something out, use the print function. Simple as that. Cool. Okay, we just did that, yeah. Variables. Now, who here's done the lab already? Really high, I want to see, come on, wake up. All right, cool. So everyone who hasn't, Variables are new. For those of you that have done the lab, well, you're already experts at this, so, now this is just a refresher for you. A variable, it's kind of like math, where when you've got a value, like, variables, just like math, right? F of x, so, x is that variable. You can put in whatever you want. It's a stand-in for something, right? That's what variables are in the computer. Or we can think of them as like little boxes to store information for later if we want. So here on that one line there, a equals 5, and m equals the string, some string. So the value 5 on the right-hand side of that expression there is the literal 5. And I'm saying, okay, variable a, you now also have the value 5. The next line, there's the literal some string, and we're putting it into the variable m. Here, I'm just going to copy this. Great. Now, if I go down here and say print a, what do you think I'm going to see? You may have never seen this before, but I'm willing to bet you'll guess what it is. Someone yell it out. You'll see a. No. I mean, maybe. Is that what you meant when you said A? Not really? All right, you get it now. It clicked. Who here was like, yeah, that's what's going to happen? Come on, wake up. If your hand's not up, that means I'm going to assume you don't understand anything so far, which is really concerning for me. I mean, only raise your hand if you actually do understand. What about M? What are we going to see when I say print out M? Is that what you thought? What about this? Z. What do you think I'm going to see if I print out Z? What the hell's Z? Yeah, because I didn't define Z. I said A, okay, A, you exist and you have the value 5. M, you exist and you have the value some string. Now, going back to that example before, where I also printed out the type of A, here's where type can be a little bit more handy. I've just got some variable A. I can't tell what its value is just by looking at it. So if I want to know what its value is, I could just print it out. Oh, it's 5, great, right? I realized, yeah, on the previous box I just said A equals 5, but imagine that was like a billion lines of code before and I forgot what it is and I'm like, what's A printed out? Oh, okay, it's 5. And what's its type? Oh, it's an integer, great, yeah. Yes, 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 yes. Yes, they absolutely will. The only way to get rid of it is if you reset your runtime. Let's see, restart runtime. Yes. Initializing, okay, great. So now, if I don't run this cell, and I hit run, it's going to say, what's A? Well, oops. It's going to say, what's A? Well, I didn't define it yet. I'd have to hit run here, and then do that. By the way, look at this. You know how I say Google it? Look what Colab's even doing for you. Oh, here's a bug, and it's like, do you want to like Google it? It's even doing it. It's made it even easier for you. It's not just me telling you. Google Colab is telling you to just Google it. Like, what went wrong? I don't know. Check it out. So here, I'll run it. So now A is in fact 5, and there we go. Cool. Now, here is a big warning. Raise your hand if you want to be a math major, or you are a math major. 1, 2, and a half with your hands? No? Raise your hand if you're taking math classes right now, though. Yeah, okay, great. So, here's a big warning. Equals means something very different in math than it does in programming. A single equals means assignment. It doesn't mean equality. It effectively means that it'll be equal after the assignment is done. But when I said A equals 5, I'm not stating a fact. I'm not stating, oh, A is equivalent to 5. I'm saying, no, A, go into 5. It's assignment. If I really want to check if equality, I use a different operator called equals equals, which actually checks if it's equal or not. Let me make it a little bit more obvious by maybe. If you're a mathematician and you look at that little cell of code there, you're going, what the hell? That doesn't make any sense. A is equal to 5 and also equal to 77. Well, it doesn't make any sense at all. But to a programmer, that means, okay, on line 1 there, I put the value 5 into A. And then on line 2, I put the value 77 into A. So the 5's gone. I just overwrote the 5. So when I print out A, the value we're going to see is whatever was last there, 77. It's because it's assignment, not a statement of equality. Because if it was, this is absolute nonsense. But to a programmer, no, it's perfect. It makes perfect sense. So just a warning there. So using a variable. I'm just going to copy this. The first print is 5 plus 6. What's 5 plus 6? Somebody be brave and yell it out. 11. Great. And so that's that first thing, that first 11 we see printed out, that's that 11. Then on line 3, I say A equals 5. So what value does A have? 5. B equals 6. What value does B have? 6. Oh, okay, great. So then on that last line, I say, okay, A plus B. Well, what's A? What's B? What's A plus B? 11. Say 11. There you go. Print it out. Oh, there we go. So it acts the same way now. That variable took the value that it was assigned to and just was that value. So A plus B is 11 because A was 5 and B was 6. So there, we're starting to use variables. So yeah, here, I've been talking for a bit. Take a moment and do this activity. Who's got the computer? Yeah, do this activity here. Assign various values of types, strings, integers, floats to variables. Try adding them together. Different types, what happens? Try this. Figure out how to display the contents of a variable. That one's kind of a freebie. So have at it if you've got your computer. If not, maybe work with someone next to you so you can see and explore. Raise your hand if you're done. Raise your hand if you'll be done in like 30 more seconds. Cool. Take 30 seconds. All right, if you look at my code, I created a total of 6 variables. I called them var1, var2, var3, var4, var5, var6. The previous examples I had the variables, they were all one letter. Obviously, you're going to run out of letters pretty quick if you just use a single letter. So here I call them var1, 2, and so on. 1, 2, and 3 is a string, an integer, a float. 4, 5, and 6, string, integer, float. So the first thing I'm doing there is I'm adding 2 strings together. And what do I get? What's the result of adding 2 strings together? This really isn't a trick question. What happened? It combined them. It concatenated them. And it gave us back a string. What about it? Can we subtract them? No, that doesn't make any sense. Multiply them? No. Division? No. All right, well, whatever. What happens if we do var 2 and 5? 2 integers. What happens if you add them together? Well, we get their sum, just like you would expect. And same with all the other arithmetic operators. They all work just fine. Let's do the floats. 3 and 6. Let's do plus. And yeah, those work as well. And same with like division and whatnot. We're all good, as you would probably expect. And interestingly, you can take a float or an integer and add it to a float just fine. Although something interesting just happened there. First and foremost, ignore the fact that it said blah, 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 0.00000002. Ignore that little 2 for a moment. We'll talk about that shortly. But 77 plus 123.456 is 200.456. So you can actually add integers and floats together, and it's going to work just fine. Same with multiplication. But notice it took an integer and a float, and what did it give us back? What was the type of that result? Float. I know because it's got decimals. Great. Var 3 and 6. Let's see if that works just fine. Okay. Okay, what was it? 2 and 3 gave me a funny result. I'll take a moment to talk a little bit about this. So, computers are really bad with decimals. Floating point numbers, it has a really hard time with it. So much so that, I mean, you look at that, we know the answer to 77 plus 123.456 is in fact 200.456. But is 200.456 equal to 200.4560000000002? Are those equal? No, of course not. They're not the same. So what the hell's going on? Computers suck with floating point numbers. They really do. We've got some tricks for dealing with it. But this is what we call a floating point precision issue. I didn't mean to talk about this today, but I'll very briefly talk about it, and then I'll talk about it a little bit later in the course when it comes up. Basically, the issue is, I'm gonna quiz you all. What comes after 1? What comes after 2? What comes after 3? What comes after a billion? A billion and 1. What comes after a cajillion? Cajillion and 1, right? I mean, it's easy. Okay, that's integers. Let's talk about floats now. Real numbers, for example. Let me talk about real numbers. Real numbers are numbers with decimals. What comes after 1? Come on, what comes after 1? People are kind of like grimacing. What comes after 1? Yeah, we got a bit of an issue here. So, look, we can count towards infinity with integers, right? We can just keep going. Because as soon as someone says, oh, here's the largest integer, I go, no, here's that number plus 1. And, it's always going to get bigger. And there's an infinite number of them. But this is what we call countably infinite. We could put our finger on each one as we go. It would take us forever, but we could put our finger on each one. Now, obviously, that issue arises with real numbers. It keeps going. But the issue is a little bit funny with real numbers because, well, there's also like an infinite number of numbers between 1 and 2. Like you were saying, like an infinite number of zeros and then a 1. Right? Which is, of course, also a ridiculous statement, but that's kind of the idea. What comes after 1? 1.1? Well, what about 1.01? What about 1.001? What about 1.000, and so on and so on and so on. So the problem is there's a lot of decimals. And the issue for the computer is it really can only hold a finite number of things in it. Right? Everything is stored in like series of transistors and whatnot, right? We're not going to get into the nitty-gritty details of that. Now, there is a finite maximum number that your computer is happy with. There's ways to make it deal with bigger numbers, but by, out of the box, your computers can only store like what's 2 to the 32 now? If this was like 15 years ago, your computers really would only be happy with that number of unique integers. If you had a number you wanted to store in your computer that was bigger than that, you'd be in trouble. Today it's a little different. We use 64. Come on. So it's a lot bigger. But the point is there's still a finite number of integers that the computer's happy with. There's a finite number of floating point numbers that the computer's going to be happy with. But there's a hell of a lot more of them. So we got to, long story short here, the way that our computers are designed is we kind of go like, well, we're going to have to kind of forget about some of those decimal numbers and just kind of, get close enough because it is what it is. So that's the quick answer of what the hell just happened here. Now, of course, if you're left going like, but what if I wanted to check if my numbers were equivalent? Is it going to be happy? And the answer is like, well, with Python, maybe. Other languages, yeah, it's not going to be happy. It's going to say they're not equal. But the trick that you would do, I'm going to explain this right now. I'm not expecting this to stick with anybody unless maybe you know a little bit more programming already. We will come back to this later. This really won't become an issue in this course, though. I'll just explain it for completeness. The trick you do is you check if the difference between what you got and what you want it to be, you check if the difference is below some threshold. So here I would be like, are the numbers the same within a threshold of like 0.00000001? And they'd be like, yeah, they're the same. Because their difference is smaller than that. Anyways, any questions about that? It's really not important for right now. I just explained it because why not? All right. Different types. But of course, who tried to do var1 plus var3, right? Who here tried to add the string to the integer? It's not going to happen. Who here tried to multiply a string in an integer? Anyone try that? What did you get? Oop. Let's see. Well, I multiplied the string hello by 77. Who wants to take a wild guess without going through and counting what it did, though? Use your intuition. Say it? What?
It added them together.
Yeah. It concatenated them so there's 77 hellos now. Cool. Great. I don't know where this is going to be useful, but maybe it will be later. I don't know. But you can do it. What about division? Can we divide? Does that make any sense? No, it doesn't make any sense, because what would that even mean? Multiplication was kind of a weird one, but I guess like once you kind of see it, you go like, all right, yeah, fine, cool. Because you got to remember, someone somewhere told the computer what to do when you multiply a string and an integer. And someone said, how about we do this? No one showed up and said, here's what we're going to do with divide. Maybe someday someone will. I can't think of where it would be useful right now, but maybe someday someone will. And then from now on, everyone will do it that way. But anyways. Who here tried number 4? What did it do? Was it happy? It was not happy. 5 equals a. It's going to say, well, I cannot assign to a literal. I can't take the value 5 and assign it anything. Whenever you're doing assignment, the thing that you're putting it into is on the left. The expression that's ultimately going to crunch down to a value is going to be on the right. So here I mixed it up, and it's like, what? Now you'll see it said maybe you meant equals equals. That is if you're checking equality. We'll learn about that a little bit more in detail a little later. But yeah, it's just wrong. And who here figured out how to get the value of a variable that you want to know? Like who here figured out what's the easiest way to just know what value a variable is storing? It's not really a trick question, but you all know the answer. It's not any more sophisticated than stuff we've already been doing. You just print it out. And it's for that reason why print is going to be like your best friend. When you're writing code and you're like, okay, crap, what value does A have right now? Just ask, print A. Oh yeah, that's what it is, yeah, good. Any questions before I carry on? Yes?
Can you assign a variable a function, like say x equals print, so you don't have to type print out?
So, okay. Yes, in Python, yes. Not in many programming languages you can. In Python, you can. And I'm going to show you, for the sake of showing you, I don't recommend you do this. There's a time and a place for this. But if you do this now, chances are you're going to get like mixed up. And you can also overwrite what functions are to really mess things up. But just for the sake of showing you, I can say x equals print. And then I can say x hello world. And it's hello world. Because now the variable x took on the same function as the variable as the function print. Cool, right? But there is a time and place for this. At this stage, pretend there isn't. Now here's where you can really mess up. And people do this all the time. So I'm going to show you because you might recognize that you've made this mistake in lab or on an assignment or something. Is if you show up and you say print equals, no, let's say type equals 55. Actually, let's see, will that even work? There, type is 55. But a moment ago, we just used type as a function, right? We asked, type told us what the type of a value was. So if I say print type of 55, it's going to give us an issue. It's going to say int object is not callable. And you're left going like, what? That doesn't make any sense because type is a function in 50. What did I do wrong here? I just ran this code a moment ago and it was happy. It was fine. Well, watch what happens if I just say print type. It's 55. I overwrote the function type with the value 55. That's not particularly useful, and it's a recipe for disaster. If you ever, this happens a lot with print. People, new programmers in Python will assign print to something by accident. If this ever happens and it's giving you bizarre functionality where it's like, it's just print, why isn't it working? The easiest thing to do is just reset your runtime. And that'll just obliterate all of the weird mistakes you may have made and just start fresh. Although, of course, I just messed it up again because I told it to run everything again. So let's restart runtime and not do it this time. Fun question, though. Good question. Other questions? So naming variables. I had var1, var2, var3, and like A, B, C. These are terrible variable names. They're fine for a quick and dirty demonstration of something. But remember, typically we're writing code to solve problems. And typically, if I'm storing a value in a variable, that variable has a meaning. So consider, for example, I wrote some code to do some calculations on density. And I want to store the density value. A good variable name is density. Density equals 5. Okay, great. If you don't know what my code is doing, but I give it to you and you see the first line of code is density equals 5, you're immediately going to have context. You're immediately going to go, oh, there's some density of something is 5. Where if you just saw a variable called d equals 5, I'd go like, I don't know what the hell's that. I don't know what it's supposed to be doing. Variable names must be descriptive. They don't have to be in the sense that the code will still run, but they have to be in the sense that otherwise you're going to make every other programmer on the planet very mad at you. So have good variable names. Things like ABC, not good. If you're worried that, well, my variable name is too long, no, it's not. It's fine. It can be as long as you want. If this was 40 years ago and we were using computers that were absolute garbage and we were actually worried about the amount of space our programs were taking up on the computer, and a shorter variable takes up less characters, and less characters means less space. I'm worried about all those bytes I have to store. Fine. Today, no, you don't need to be worried. Especially when you're not even running this on your computer. You're running it on Google Colab. You're using Google's like literal supercomputers to run everything you're doing. They can handle a large variable name. So don't be afraid if your variable names are long. If they're descriptive, that's what makes people happy. There are some restrictions on what you can call things. First of all, variables can't start with a number. And there's a limit on the number of like non-alphanumeric value, like things you can include in the variable. Like your variables can't contain an exclamation point. But that's really not that limiting. The one thing where you might feel limited is there are some reserved keywords in Python. One example is def, which we're going to learn about very soon. But if I tried to use def as a variable, it's going to go, no, that's not how you use the keyword def. Because def already has a meaning, so you can't override it. But this is really not likely to cause an issue for you. And here's a convention. No, it's not it's a rule. It's a rule that if you break, your code will still work, but everyone will hate you. And I'll make fun of you, and I'll make you feel really bad about yourself. Your variables in Python, the convention in Python is what we call snake case. It means everything's lowercase, and you separate words with underscores. That's snake case. The alternative is something we call camel case, which is like where you don't include spaces, but like a new word starts with an uppercase, but it always starts with a lowercase. That's camel case. We don't use camel case in Python. Other programming languages, you use it. If you do use camel case in Python, it'll work. But if you show me your code and there's camel case, I'm going to run away from you because you're committing an egregious sin. So there are some rules that if you don't follow, Python will just give you the middle finger. And there are some rules that if you don't follow, Python will work, but I'll give you the middle finger. So be aware. There's the difference. And then constants. Here's an exception to that rule. So a constant is a variable. But the idea behind a constant is, with a variable, I can assign a value to a variable, and then maybe within my code some calculations are being done and the value in that variable is being updated as it goes. The code itself might be altering the value of that variable. I'll show you an example. If I say a equals 7 and then a equals 7 times 10. Here's a quiz. What is going to be printed out when I hit run? It's not a trick question. And here's the thing. There's no trick questions in programming. It's what are the rules we've all learned and what happens if I put them together? Computer scientists are too stupid for any tricks. chances are too, and I talked about this in lab the other day, chances are too, if you're really stuck on a problem, you might be overthinking it. That's another big new programmer blunder, is thinking too hard. Computer scientists are stupid. If you're thinking too hard, you're definitely not going to get it right, because I wouldn't be able to think that hard. So what's the answer when I hit run? Yell it out. I'm hearing non-confidence. Okay, let's work through this one. What value does A have after line 1? Okay, the 9, 2. I'm saying A equals, oh, wait. Here's what actually I meant to write. It will function the same way, but this is far more interesting. Remember, we evaluate the right-hand side first. So what is A? And what is A times 10 then? And where did I put that 70? Come on. With enthusiasm, come on. Let's try that again, where it's not just one person speaking for the whole class. Where did that 70 go? That was kind of better. Back into A. So what happened to the 7 that was in A? It's gone. It's cut. Yeah, it's gone. It's no more. That's fine. But this is an example of, okay, and I hit run and we see 70. Great. But this is an example of code that's modifying the value of a variable. A constant is a variable, but the spirit of what the constant is you set it. You as the programmer can set it, but the code is not to modify the value of that variable at all. In some programming languages, when you make a constant, if your code even does try to modify the value of that variable, it won't run. It'll be like, nope, can't do it. You said that was a constant, and your code changes it. No good. Something went wrong. In Python, it'll let you do it, but you're committing a big sin. It's a convention that if you break, everyone hates you. So a constant is the idea of you can set a value once and it's good to go. So imagine you see this there, right? Who here's from Nova Scotia? So you all know we have horrible sales tax. It's 15%, right? So we know what this means. Some bill, 1045 times 1.15, that'll tell you what the bill is with sales tax. And the next line there we go. But let's say we go down to some state with ridiculously low sales tax and I show them this, they're going to be like, what's 1.15? What is that? I don't know what that is. Well, what we could do is we could assign a constant sales tax to be that, and then the person will see some bill 1045 times sales tax. Now, there's no guessing. What was 1.15? I mean, maybe we knew, maybe we didn't know. But what is 1045 times sales? Oh, I now know exactly what that 1.15 was. It's a sales tax because it gave a label to a value. That's an amazing use of a constant. And also, I might have a billion lines of code here. What happens if the government lowers sales tax? I have to go and change every line of code? Well, with the constant, all I have to do is go here and just change it to a 4, and I'm happy. So the constant allows us a way to quickly change some important value, but it also gives us a really handy way of giving a label to a very important value that might not be obvious by hand. Like if you saw 3.1415 as the literal, you'd be like, okay, that's pi, right? Fine. But there's a lot of values that might have meaning where if you use the name of that value, it conveys more meaning. So sales tax is a good example of, it's sales tax. But what's different about the convention for snake case with this constant? It's all caps. You still use underscores, but constants are all caps. So when another programmer sees that sales tax, they go, oh, that's a constant. Don't touch it. Again, Python will let you, and it'll be fine with it, but everyone will hate you. And I think that's a great place to end today. Now, remember, if anyone has any questions at all as we're going through the course, there's a lot of resources made available to you, but the big one is student hours. Make sure and come see me in my office during student hours times. Happy to have a chat. Remember, you don't need to make an appointment. The point is you just pop in. Okie dokie, okie dokie.